Now we will continue looking at using a holdout sample or a test data set to test our models, but now we're going to expand it to our insurance data set from the previous lectures. So let's start off by, this is essentially the same code that we used in the previous lecture, but a few minor adjustments have been made. So let's start off by just reading in the necessary libraries. There they are. And let us set our random number seed. We can set it to any number, any positive integer we wish, but we're going to set it to 1, but we can set it to anything. Let us set the path and the file name, and let's read in the data set. And let's make sure that the data set got read in correctly. So let's look at the structure of the data, and let's also do a quick summary of it. So the structure of the data up here is, we have all these variables from before, and this will give us the minimum, the maximum, the mean, etc. And you can see we don't have any missing values because we fixed them earlier. Now, let us, you'll notice that in this data set we have, again, from before, 2 targets. We have a flag, did the person crash their car? And the other flag is, what did it cost us to fix the person's car? If it's a 0, then the person didn't crash their car. And if it's a 6,870 or any number, that's what it cost if they did crash their car. So we have to get rid of, we're going to solve for this guy, the flag, so let's get rid of this guy right here. We don't need him. So we're going to copy the data frame into another data frame that we're going to call data frame flag. And then we're going to get rid of the amount by setting it to null. So let's do that real fast. So if I do, head data frame flag, you can see that the amount is gone, and the only thing we have left is this flag that says, did the person crash their car or not? Okay, so this is all standard stuff that we've done before. Now we're going to introduce the setting this a train and a test data set. So here is our friend, the code for creating a flag. Let's execute him. Oops. So incidentally, if I type in flag here, it's going to give me all these true and falses. Let's see if I can just do. See, this is true, 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 false, true, false, false, true, true. These are the guys. This is going to decide which data set they go into. And you can see here we have the train and the test. Now, if we look at them, here's the dimensions of all the data. This is the dimension of our training data, and this is our test data. And you can see that if we add these two guys up, the test and the train, it goes to a, it adds up to all of our data. Now you can see here that 70% of our data will go into the training set and 30% will go into our test set. So now we're going to, if you recall from the last section or the previous week, we built 2, not 1, but 2 models. We built a decision tree, and we told the R programming language to build the decision tree and to make its splitting rules based upon a Gini measurement. And we also built another one, and we said split based upon entropy information. So let's do that again. And we also said don't go any deeper than 10 levels. So let's do that. And so there we have it. We now have two decision trees. And in what we do here, let's just for a quick recall, is this is the command right here that builds the decision tree. We're using our training data set. We are telling R to build a, to try to predict the flag, yes or no. This little dot says use all the variables. We're saying control test set, and so we can say we can tell R all sorts of things that we want to set in the data set, or in the decision tree. At this point, the only thing we're telling R is don't go any deeper than 10. But there's lots of stuff we can tell it. This is a classification problem, a 1 or a 0, and we're telling R that to split based upon the Gini rules. And everything is getting shoved into T1 capital G. And if I typed in T1 capital G, this will give us actually all the rules that R has come up with. But rather than looking at the if-then-else rules, it's sometimes easier to just look at a plot. So let's look at the plot and look at what variables are important. So here's our decision tree here. This is the Gini coefficient. And if we come over here, we can see what variables are important in order, like the oldest claim, the claim frequency, et cetera, et cetera. These are the things that decide whether or not you're going to crash your car. Like, we don't need to look at that. But here's our decision tree. Now, we can also do the same thing again with our friend, the entropy tree. And there you go, a slightly different tree. Now, they're both predicting who's going to crash their car. But the question is, which one is better? Well, the first thing you want to do before we even try to predict which one is better is you want to see how did the tree do on the training data. So let us predict using our Gini tree, and we use our training data set. Let's predict and put all of our predictions into this variable PG. And then we are going to build ourselves this code right here is going to help us build a ROC curve. We talked about this before, we won't go into it again. Then we're going to do the same thing with our entropy tree and our training data. And then we're going to plot our ROC curve to see which one is better. So let's do that right now. So looking at just the ROC curve, you can eyeball this thing. The green one is the entropy and the red is the Gini. And just eyeballing this thing, it looks as though the entropy is a little better. The red guy is a little bit above green right around here. It'd kind of be nice if they were both, if green was better all the time. But we'll look at that in just a minute. But now we're going to want to, now that we can see that both of them did a pretty good job at the training data, the real key is, let's also calculate the area under the ROC curve. So you can see that the Gini coefficient has a 67% ROC index, and the entropy has a 72. So entropy is better. But now let's look at the training data, or the test data, excuse me. Let's do the same thing again, only now we're going to give it test data. This is data that the decision trees have never seen before. So let's see how they worked. We're going to run the exact same code, only now we're going to do it on new data. And again, the entropy did better, and his area under the rock curve was 66 and 72. It's essentially the same. So, I mean, it's not the same, you know, entropy is better, but it's also the same as we got up here, 72 and 67. And this is 66. So they're roughly the same. So this is telling me that the model is not overfit because our answers are about the same. And the fact that we got a nice curve here suggests to me that we're not underfit. What I would like to do is maybe see if I can improve this code a little bit. So let's change our, let's give the decision tree a little bit more to train on. Let's go 80-20 this time. And let's run it again. Okay, so now we have 6873 on our training data, and now it seems like we've got a better entropy. It doesn't seem like there's any time where Ginny is better than entropy. It looks like they're both about the same, and then entropy just beats them, and that's good because now we have a clear winner. Let's take a look at the test data. This is the real decision as to which one is the better. So let's do that real fast. And again, the entropy is clearly better than the Ginny, and 7265. Now, what I would like to do is let's run it a few more times. So let's run it. What I like to do is run this thing several times just to make sure that it's, you know, it's correct. So I'm going to do this again. And just looking at the test data again, look at that, he's much better. And if we do it one more time, well, heck, I can just paste it again. Nope, look at that. It looks like for this case, it looks like Ginny and entropy stayed neck and neck for a while, but then entropy took off. And so 67, 72. It just looks essentially at this point that entropy is consistently better. There's times when Ginny makes a good fight of it, but when the day is done, if you're asking me which of the two is more accurate, I'm going to have to go with the entropy. So sometimes with different data, maybe Ginny's better. There's never one that's always going to be better, but in this data set, entropy seems to be winning. Another thing that I might like to do here is I might actually like to look at the tree that's coming out of this thing. Let's just see, where's our friend the tree? Right here. So here's our entropy tree. Let's just print that guy off. So what I like about this entropy tree is it's just so simple. The first split here is on urban equals 0. Well, if it's that urban means city. So if the guy doesn't live in the city, we go this way. And it comes down here, and the chances of crashing his car went from 27 down to 7. So if you live in the country where there's nobody driving, you're never going to crash your car because there's nobody to crash into. Well, wait a minute, I live in the city. Okay. Do you have a salary job? Are you a doctor? Are you a lawyer? Are you an engineer? Yes, you go here. You don't crash your car as often. Why? Because you're not traveling in rush hour traffic like you might if you were like in rush hour to go to a factory or something where there's lots of cars going in there. You're more likely to crash your car. You got more opportunity to crash it. Then we go over here, and it says, do you have an expensive house? So if you got an expensive house, then yeah, well, in that case, you're probably wealthy, you don't drive in rush hour traffic, you're less likely to crash your car than the other people. You're still more likely than the average, but okay. So we got a person who's, you know, less expensive house, he's more likely to crash his car. Then we say, well, has your license ever been revoked? Yes, over here. So if you live in the city, you drive in rush hour traffic, your license has been revoked in the past, yeah, you got a 76% chance of crashing your car. But no, it's never been revoked, but you got a lot of traffic tickets, again, you're going to crash your car. So this tree is a simple tree. I like it. It's easy to understand. So because I like this entropy tree, what I would do in a real world situation is I say, okay, now that I know what tree I like, I'm going to build a decision tree on all of the data. And I'm going to probably use this guy right here, the entropy one. But let's build both. It doesn't cost us anything. So we're going to build both trees, only now we're going to use all the data because now we've decided that the tree is good. It's not overfit. It's not underfit. It's a good tree. We're going to build it, and we're going to use all the data. And let's just take a look at our friend, the entropy tree. That's the one we're probably going to go with. Let's just see if it looks I would hope that it looks sort of the same as this guy. Now let's see. Look at that, urban, salary, home value. It's almost the same tree. I mean, I think that this number might have changed, maybe the house value a little bit. But the point is, it's essentially the same tree. And then the other thing I might want to do is see, is it going to look approximately the same as it did before? So let's just, for fun, oops. Run everything again. You can see that our area under the rock curve is consistently in that 72% range. Let's take a quick look at the rock curve. Again, it looks like it did a nice job. It lost a little bit to the Ginny guy here, but for the most part, he was a better predictor. My personal recommendation would be I would go with the entropy tree, and I'm confident that the tree is not overfit or underfit, and that it is an optimal fitting of this data.